So here I'm going to be talking specifically about the Hertzsprung-Russell diagram, which has proved to be invaluable in classifying stars and being able to find out different things about stars which are really far away. Here there are some points that you need to make sure that you understand. I'm going to use a diagram from our textbook to discuss it. This is one. There's many of these diagrams, and some of them are slightly different. But this is an example of a Hertzsprung-Russell diagram, and just a few points to make sure that you understand. On the horizontal axis here, I have got the temperature. This is in Kelvin. And we have got what we call the spectral class. Remember the O, B, A, F, G, K, M, which basically all stand for different color stars. Now our sun is in this region over here. As you can see on the vertical axis, on this right hand vertical axis, we have got the luminosity relative to the sun. Do you notice that? Here we've got the luminosity relative to the sun. So here we have the sun. This is one solar luminosity, and if I go across here, we get, this is the area where our sun is. It's a type G star. It's a yellow star, and it falls within what we call the main sequence. These are all your hydrogen, typically your hydrogen burning stars. They're in the main part of their life. This is, the sun will be in this main sequence for probably another, say, 5 billion years, and then the hydrogen will run out, and then it will move, and we'll discuss that another time. So these are your main sequence stars. Now, scientists have been able to, by looking at different types of stars, looking at their color and consequently their temperature from Wien's law, they have been able to put them into this graph. And this is, as I said, has proved really important. Now, we're going to discuss this over here later on. I haven't actually discussed this idea of absolute magnitude, but this is the apparent magnitude as if the star were 10 parsecs away. So when you have a look at that, you'll understand this better. Our sun, for instance, would be about +5. So if our sun was 10 parsecs away from us, it would have an absolute magnitude of, an apparent magnitude of +5. I'll discuss that in another video. So what's really important about this diagram is that scientists and astronomers can identify a star, and they can by looking at the radiation from the star, from looking at its spectrum, they can see what color the star is. And from that, say if they get a star like this, they say, well, it's about 7,500 Kelvin. They can go up here and they can say, well, we're about over there, and therefore we have a luminosity of about just above. This is actually about 5. Notice an important thing, that this is what we call a log scale. This one is, as I said, is the luminosity of the sun, which is about 3.9 times 10 to the 26 watts. Each and equal distance is actually a multiple of 10, and then the 10 is multiplied by 10 to be 100. So it's a logarithmic scale, and in the reverse again, we are dividing by 10 again, and dividing by 10 again. So this star over here is about 1,000th of the luminosity of the sun. Another important point to realize with this Hertzsprung-Russell diagram is that the temperature and the color gives a very clear indication of the mass of the star, because high mass stars over here, for instance, let's say we've got a type B star. These are our high mass stars. These are massive stars. There's massive pressure from gravity, which is causing a huge amount of nuclear fusion within the core of the star, giving out huge amounts of energy. Because of the high pressure, that energy is causing light to have a short wavelength, different color, is like a bluish whitish, and then therefore these will have very high luminosity. They're also relatively short lifespan stars because they're burning up the energy so quick in this region. They tend to last quite short. Further to this, we get these stars over here, which are very important. These are our supergiants and giants. Now they all fall down here, which is in our red region, orange red, and so we usually call them red supergiants or red giants. Now these are stars that have come out of the main sequence, so they finish burning their hydrogen and they tend to move in this direction. I will discuss that in another video, that whole final death of a star, in which way it can go. But these become very big, so they're actually very luminous. As you can see, they're highly luminous, but they're relatively cool. The surface temperature of them is relatively cool. So these therefore must have a very high surface area. Remember, the luminosity, according to Stefan Boltzmann, is sigma times A times T to the 4. Now, the temperature is relatively low, so the area must be correspondingly very big. And so these are really big red. Up here, because they got such high luminosities, look at that, 100,000 times more luminous than the sun, but the temperature's low, so the size of them is truly huge. They are massive in comparison to our sun. So these are some points with this Hertzsprung-Russell diagram, really useful in being able to find out the luminosity and the temperature of a star. Once we know the luminosity of the star, if we know the luminosity from this formula here, B is equal to L over 4 pi d squared. We can measure that. We can measure the apparent brightness of the star. We can get the luminosity from our Hertzsprung-Russell diagram. We can calculate an idea of the distance that the star is away from us. So it's a good way to measure how far a particular star is away from us. Okay, so I'm going to leave it there. I hope you found that useful.